law, and this is my magnetic braking lab for Physics 2212. The purpose of this lab was to explore Faraday's law by observing a magnet falling through a conductive tube of aluminum foil. A time-varying magnetic field provides an EMF that can drive current. In this lab, the source of the external magnetic field was the bar magnet, and the induced current was driven around the tube of aluminum foil. I then modeled this interaction computationally. I concluded that the aluminum foil tube slowed the rate of the falling magnet, and from my experimental results, it took 1.27 seconds for the bar magnet to fall through the tube, while it took 1.12 seconds for the bar magnet to fall from my computational results. Some of the physics principles highlighted through this lab are Faraday's law, which states that a changing magnetic field can induce a current in surrounding objects, the Biot-Savart law that helps us find the magnetic field of a bar magnet, and Newton's second and third law, which dealt with net forces and directions. After recording and averaging the times for 5 trials, it determined the average time it took for the magnet to fall through the tube to 1.27 seconds. Here's some additional data on the length and radius of the tube, the width of the foil, and the magnetic dipole moment U calculation from Lab 3. Lastly, I have the mass of the bar magnet. The code is divided into multiple steps. Step 1 contains the measurements of the tube, including the length, width, and radius of the aluminum tube foil. Step 2 is regarding the magnetic field function of the bar magnet, which I borrowed from my Lab 3 code. Step 3 was the magnetic flux function. Step 4 dealt with the current in the ring. Step 5 dealt with the magnetic field at each ring. And the last 2 steps dealt with the magnet's net force, velocity, and position. Here you can see my computational model results. On the left, you can see the tube and the magnet, and on the right, you can see the velocity versus time graph, with the print box showing the result that it took about 1.12 seconds for the magnet to fall through the tube. The intensity of the coloring on the tube indicated the magnitude of the current flowing through each ring. Red and blue indicated current flowing in opposite directions. I decided that the north end would point downwards while falling through the aluminum tube, since the magnetic field points out of the north end and the magnet was getting closer to the loop. There was greater magnetic flux in the downwards direction. As a result, we know the induced magnetic field must point in the opposite direction to change in magnetic flux, meaning induced current happens in counterclockwise direction, so red is clockwise and blue is counterclockwise. If the magnet is flipped around, then the direction of the induced current would become clockwise, but velocity and position would remain unchanged, so the time to exit the tube would also remain the same. The total time in the tube for experimental system was approximately equal to the total time in tube for the computational system. To make the computational more accurate, we should have also accounted for error and conductivity resistance. The shape of the velocity versus time plot tells us that the magnetic and gravitational forces acting upon the bar magnet eventually cancel out to give us a net force of 0, as the bar magnet stops accelerating when the forces are equal, which is when it is in terminal velocity. If the resistivity of the conductor were reduced as close as possible to 0, the magnet would have fallen more slowly and completely stopped falling if resistivity was at 0 exactly. Using the formula voltage equals current times resistance, we see that if R gets closer to 0, meaning if R decreases, then the induced current will increase and get larger. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? Well, the magnet will fall faster, as less rings means you're reducing the induced current. Thank you.